In this video, we're going to look at a couple of other examples for hypothesis testing. So looking at this one, it says, a children's clothing company sells hand-smocked dresses for girls. The length of one particular size of dress is designed to be 26 inches. So we want it to be 26 inches. So that means that our null hypothesis is going to be it is 26 inches. The company regularly tests the lengths of the garments to ensure quality control, and if the length is found to be significantly longer or shorter than 26 inches, the machines must be adjusted. So in order for them to be adjusted, it can be longer or shorter, not one way or the other. So this is going to be that it's not equal to 26 inches, because anytime it's shorter, they have to be shut down, or anytime it's longer, they also have to be shut down. The most recent simple random sample of 28 dresses, so N is 28, had a mean length of 26.3, so the sample had a length of 26.30 with a standard deviation of 0.77 inches. Now it does state that there is a standard deviation, but it does not state that this is a population standard deviation. This is just a sample standard deviation. So this is an S. Anytime I have an S, a sample standard deviation, I'm going to use my T chart. Okay? So in order to use the T chart, I also will need to know degrees of freedom, which we'll get to in just a moment. Perform the hypothesis test of the accuracy of the machines at the 0.01 level of significance. So alpha is 0.01. Okay, so when we're looking at this, I know that my alpha is 0.01. I'm going to go ahead and sketch the diagram to kind of help me out here. So this is a two-tailed because it's a not equal to test. Since it's a not equal to test, what goes in here is actually alpha divided by 2. So 0.01 divided by 2 is going to go in here, which is equal to a 0.005. 0.005 is going to go in here. This is the amount in our right tail. Reason why I want to know that is this table gives me the amount in the right tail, not the full alpha, just what is in the tail portion. So we had a 0.01, but because we had to divide it by 2, we're actually looking at this column here. Looking at this column here. Okay? Now, we had an N of 28, so our degrees of freedom is going to be 27. So we're going to look at the row with 27, and we're going to stay on this row the entire time. But where these intersect is going to be my critical value, 2.771. 2.771. So I have it here, but notice I also need the negative. So my critical values are positive and negative. Anytime that you have a two-tailed test, it's going to be a positive and a negative critical value. Okay, let's calculate the test statistic. The T. It's going to be 26.30 minus 26 divided by 0.77 over the square root of 28. So 26.3 minus 26 is going to be 0.3. 0.77 divided by the square root of 28 will be 0.1455. So our T value is going to be a 2.0616, which is going to be somewhere over here. So based on the critical value, I will not reject the null hypothesis. But let's continue looking at it because we need to find the p-value. Recall that this is a t-test, so the p-value will be between two values. This is a two-tailed test, so I'm going to have to actually multiply each of these values by 2. This is 2.0616. I'm staying on the 27 degrees of freedom line. I'm going to look up a 2.0616. It's going to be about right here. Follow that up, and it's between 0.025 and 0.01. Remember, I flip-flop them, 0.01 and 0.025. Multiply both of these by 2, so I get 0.02 and a p-value of 0.05. I compare this to the alpha of 0.01. Both of these are larger than your alpha. Since the p-value is larger, as well as the test statistic is not in the critical region, do not reject the null hypothesis. So, there is not sufficient evidence at the 0.01 level of significance to suggest the machines should be shut down or should be adjusted. Now let's think about this. If they do not equal 26, that's when they need to be adjusted. But since we did not reject the null hypothesis, basically we kept, can't do that. We kept the null hypothesis. Not sure why that is being so. There we go. Okay, so since we kept this one, it is not going to be adjusted. Let's look at another example because I know that these can be extremely tricky. I'm going to go ahead and erase my markings on my T chart over here so that we can look at it cleanly. But let's look at example 3. One cable company claims that it has excellent customer service. In fact, the company advertises that a technician will arrive within 30 minutes of a service call after a service call is placed. One frustrated customer believes that this is not accurate, claiming it takes over 30 minutes for the cable technician to arrive. So we're comparing these things to 30 minutes. And we're talking about the mean, so we're going to say that it's equal to the mean. The customer is complaining and saying that it takes more than 30 minutes. So our mu is 30. The customer asks a simple random sample of 9, so n is 9, other cable customers how long it has taken for the cable technician to arrive when they have called for one. The sample mean for this group is 33.2 minutes with a standard deviation. Now notice it says standard deviation, but it does not state population standard deviation. This is strictly the sample standard deviation. So the sample standard deviation is 3.4. Assume the population distribution is approximately normal. That's just saying, okay, because our sample size is so small, we need to know that it's approximately normal. That way we can use the Z or the T. If it's not normal, or our population is too small, things of that nature, we have to use something else, and we don't want to discuss that at this point. Okay? Assume that the population distribution is approximately normal. Test the customer's claim at the 0.025 level of significance. So alpha is 0.025. So we know that alpha is 0.025. We are looking at it here. This is a right-tailed because we're talking about greater than. So let's find the critical value. In order to find the critical value, we need degrees of freedom, n minus 1. So 9 minus 1, that's going to be 8. We're going to stay on the 8 line. So let me circle the 8 line. This is where we're going to stay. And our level of significance, our alpha level, was 0.025. Now be careful, because there's a couple of others that have 2 5s in there. Make sure that you're using the appropriate number of zeros in front for this. So our critical value is 2.306. 2.306. Should this be positive or negative? It should be positive, so it's a positive 2.306. Now let's look at the test statistic. That's going to be a t. We have 33.2 minutes minus the 30 minutes that they claim, divided by the standard deviation of 3.4 over the square root of 9. So 33.2 minus 30 is going to be 3.2. 3.4 divided by the square root of 9 is going to be 1.1, and let me try that again, 1.1333. So our test statistic is 2.8235. Well, 2.8235 is going to fall somewhere over here. This one doesn't ask us to use the p-value, but let's look at it just in case. 2.835. We're looking for a 2.835. It's going to be somewhere between these two. So follow this up. It's between 0.025 and 0.01. So 0.01 p-value and 0.025. Comparing this to the alpha, you'll notice that our alpha of 0.025 is equal to this one, but it's actually greater than this one, and our p-value is somewhere between. So our alpha is actually larger, p-value is less than our alpha, so reject the null hypothesis. Since we reject the null hypothesis, there is sufficient evidence at the 0.025 level of significance to support the customer's claim. That the mean is more than 30 minutes. So you do have to be careful about the t-values and the t-scores, making sure that you're staying on that degrees of freedom line, as well as wherever you get to the p-values, making sure that you're looking those up properly. So practice a few of these and then let me know if you have any questions.